Hello. How's everybody?
Hello.
Good morning, good evening, all.
Um, okay, I'll just quickly share the link of the call in Discord in case someone needs it. The link. Okay, nice. So last week we started discussing about implementing a GPT model from scratch. Um, I had just one missing part that I think that the project will take me like 20 minutes. And then we will discuss about pretraining on unlabeled data, which is chapter 5, with the help of Carlos. And then we need to pick the volunteer for chapter 6, one of the final chapters. So let's get to where we stopped, which was here. I don't know if you remember, but remember that we started implementing the GPT architecture, or yeah, the GPT architecture by coding the GPT backbone, which was this thing that had dummy dummy blocks. So we created this dummy GPT model, which had a dummy transformer block as well as a dummy layer norm. Later, we started like actually doing the implementation of the layer norm, the yellow activation function. We use it to do the feed-forward network, and we added the shortcut connections, and then we put all together inside a transformer block. So we stopped calling it dummy, and we built the actual transformer block, which is this one. Now, we are headed to the final step, which is actually putting using this transformer block into the GPT architecture. And in the small GPT model from OpenAI, they use this transformer block that we have here 12 times. So that's what we do. The the thing that we used to call dummy GPT model is now not dummy. And basically the changes is that this here, we use the actual transformer block, the one that we just coded, and layer norm, we use layer norm that we created before. The rest stays pretty much the same as we saw. We start from the embeddings with tokenized embeddings, then position embedding, and then create a dropout, then this add these 12 blocks here. This is what this line of code is doing. That's 12 times 12 blocks of the transformer block. And then the final layer norm that is here, and then a linear norm, which is the linear norm, the linear layer, which is a final layer that is going to output a tensor with the size of the vocabulary size, since we need to pick which word is going to be the most probable one that will output. That's pretty much it. The missing part is that we we can test it and see how it performs for making text generation. So I'm gonna run that. Let me run this to make some text generation. Okay. So let's remember that for text generation, we have like a context window, and basically what the model is doing is word completion. So it generates the next token. So given this context, for example, hello, I am, the model is supposed to produce an A, and then given in the second iteration, given the context hello, I am A, the model is supposed to produce the model, and so on until it reaches the sixth iteration. That is the amount of iterations that we're gonna use right now here. So how is the process of text of text generation? We can code a simple text generation function, which basically is a loop. It's a loop that repeats 6 times, or the amount of times that we put as max new tokens. Then it takes just a sec, because I got lost. Yeah, it has a context size. So right now, context size, oh, context size, it comes from here. Okay, context size is pretty big. I'm sure in the petit, this is the size of context size. Just let me double check, because this is a thing that we, context again. Yep, 1024. So yeah, if, for example, if the context size is just 5 tokens, no, if the LLM only supports 5 tokens and the context size is 10, then we will take only the last 5 tokens as context, because the LLM only supports 5. Then we use this show documentation. This context manager, I think that's the word, context manager. We use this context manager from PyTorch, which basically what it does is that it disables the gradient. Why? Because we right now don't care too much about the gradient, since we're not gonna do backpropagation. So every time that we are fully sure that we're not gonna use backpropagation, and that's usually the cases for inference, when we want to make text generation or predictions, we can disable it. So it is more performant, and basically don't keep track of the gradients. So what this does is just disables the gradients. So we use this context manager and then pass the input to the model. We store it in a variable called logits. We care only about the last step, the step that the model produced. We pass these logits to a softmax function to get to turn it into probabilities. We use these probabilities to get the position of the highest probability value, and in this case we get the ID of that token, and we concatenate it to the initial inputs. So how does it look visually? We start with these token IDs. Well, with these tokens, these are the token IDs. We pass it through the model. The model is gonna predict something. Let's say it predicts this ID. This ID can be decoded as A. Then we append, this is what is happening here. Then we append this to the next, to the context, and we can run again another iteration. So given that now we have the appended letter A, the model can produce something different, which is model in this case. And then we append model, we run it again, and the model produces ready. And so on until we reaches the max new tokens. So if I run this, so if I run this, we get this response. Of course, this doesn't mean anything yet because it's not decoded. If I decode it, ideally we should see something that looks like this, right? Because we start with the context, hello, I am. And so we expect to see something like, hello, I am a model ready to help. But when I run it, we see something that doesn't look like that. We see, hello, I am feature and meant by something super weird. Why is that? Is that expected? Yes, indeed, it is expected. Why? And the reason why is basically what Carlos has prepared for us today, which is because we haven't trained the model. The model hasn't looked hasn't looked at any data. So we need to actually run it through data and teach it to speak. Any questions? No? Then I'll stop presenting and I'll let Carlos take it from here.
Am I sharing the right screen? I think I'm not.
We see a notebook.
Yeah, okay, I'm gonna change Teams minutes. Give me a second. I don't see what I'm sharing. I just want to see what I'm sharing.
I'm glad I'm not the only one, given we have Zoom, Google, Teams, WebEx, Chime.
Am I sharing? I think now I switch and I'm sharing the wrong screen.
You're sharing your whole screen with the GitHub repo, the previous chapters.py.
Yeah, but that's not the one that I wanted to share. What about this? Okay.
Your notebook, the pre-training notebook.
This is the Jupyter notebook I wanted to share. Let me just leave it like that. Okay, now the thing is working. And now you see this, where are we, right?
Yes.
Okay, this is fine. So this is if anyone wants to follow, I have the repository here, which is, well, I'm gonna share it on the chat so you have the link. And now I cannot find the chat. What is the chat now? It disappears. It completely disappears. The Zoom.
If it's easier, use the Discord. If you share it on Discord, and it just makes it easier for all of us. Yeah.
Okay. Okay, here it is. So just in case anyone wants to follow it, it starts, if you go to the repository, there is this pre-training Jupyter notebook at the root, which is what I'm opening here, okay? And then you have to clone it and activate a virtual environment and install the requirements and run. These two things, both the pip and the Jupyter notebook, have to be executed from the virtual environment. So you have when you open the Jupyter notebook, it has the dependencies because I'm using classes and stuff that are inside this repository, okay? So just in case anyone wants to use it to follow. And this is where we are. As Santiago said, we have an LLM model already working, but it doesn't have weights that came from a training. So if we ask it to generate something, it's just going to be like random text, basically. So from there, the chapter of today covers all of the second stage. So it's we don't have a lot of code today, but we are going to be using things from chapter 2 up to what Santiago showed today. So it's like coupling a lot of things that we have been preparing. So it's a quite a nice chapter. And what we are going to be doing is basically first, I'm going to start by generating tests. It's a part that is pretty similar to what Santiago did, but just to show that why do we have random text. And then we're going to need to write something we're going to need to be able to evaluate that text and kind of numerically see if it was good or bad. That's where we are going to start first doing some numbers on the tokens that are generated. And then we're going to use that to generate an actual function that can be used as the loss to make the calculation and to be able to tell our model every time that it generates a text when we are training, we're going to be able to tell it, this is what you should have done. And it needs to be able to have like a measurement to obtain a number, that's the part that is a little bit weird because we are generating some text like every effort moves, and we want it to continue generating the next part of the text. So we are going to basically tell it the answer. The answer is going to be the next token for each of the words. So for every is effort, for effort is moves, and for moves is, we know that it's you because we decided it. But we have to translate this into something numerical. So it can actually compute a loss and then trigger all the back propagation. So we're going to be doing that. Then we're going to write a training function, which is basically we're going to use the verdict, the text that we used in chapter 2 to actually run a loop and train the GPT with some text. Then we're going to do some generation strategies, which basically means we're going to generate text, but the model, every time that we run it, is going to be giving us the same result. So we want to do something more flexible than that. And finally, we're going to see how to load and save the weights and load the OpenAI weights. So we can have an actual really well-trained model. So to get started, we have, I'm going to be using basically this dependency. The warning is just because every time I run Matplot, it shows a lot of warnings. So if I run, let me just restart the kernel. So we have like a fresh execution. The warnings is just because I run these filter warnings, and it's going to be the output is going to be a little bit cleaner. But here's where we start. The chapter 5 starts by basically simulating some sort of training set, but very, very tiny, with only two samples from a batch. And these are the ones. We have first two inputs, every effort moves, and I really like, and then two targets, which are the targets for each of them. Which is for each sentence, which would be the next token. And we're going to be using that. First, I have this GPT model, which is exactly what Santiago left, with what we prepared on chapter 4. And I'm going to be instantiating this. And now we can do, this is repeating exactly what Santiago did, which is to, I did not execute this. Sorry, let me just do this. Okay, so this is basically like doing the same steps that we did that Santiago did before. which is to use the model to generate some logits, and then using softmax and argmax, we get the text. And if I show it, it's something that it does not actually make sense. This is the output for the first input, and this is the output for the second one. It's basically nonsense because we haven't trained it. And what I did here, this is basically showing the logits and the softmax of the logits, which are meant to be something that we can interpret as probabilities for each of those tokens. And what we see is that the probabilities of getting the right target that we actually want are random numbers. To prove it, I created these plots, which is basically what we are getting is the probabilities of the targets, not the probabilities of the things that were actually outputted, but the one that we wanted. And I'm plotting them. First, I did this plot, which is just plotting the 3 values for each of the words. But then I found that this doesn't give me much information. I mean, I know that like apparently is more likely to be used as a word than chocolate, but I needed a little bit more context. So what I did is I created this other plot, which gives me the 3 words of our targets, which is effort moves you, the word that we want to find. And then it chooses how many? 33 random words from the entire vocabulary, and it shows me the probabilities. So now I see that the system can probably give me cart or yo or whatever. If I run it more times, the 3 words are going to be static effort because these are the targets that I want, and the other ones are just random words. So what we see here is basically the reason why if we run our model, it's going to give us random text because the weights are basically random yet. So the same thing happens for the other ones, for really like chocolate. Apparently like is a very likely word, but also inel, which I don't even know what it means. So we have to start telling our system, basically we have to train it because otherwise the probabilities are all random. And the most interesting part, I think, of this chapter is to actually choose a way to measure how good or bad something was. Basically, what we are doing, we're going to be telling it what's the good answer, but not what are the wrong answers, because basically the wrong answers are all of the ones that are not the good ones. So what we want to do is to tell it that whenever we give it the input that we were giving it before, which was every effort moves, then for every it's very likely that the next word is effort, and for effort is moves, and for moves is you. Basically, we are telling it when something is good. And the way to do that numerically, Santiago is using this algorithm, which I'm going to stop a little bit here because I think is where the meat of the chapter is. And also, if someone wants to stop me here, it will be very interesting because this is what took me most time to understand. And it's not like my field, so just interrupt me if I say anything wrong. But the algorithm is, we have the logits, that's what the system is giving us. We already use the softmax to convert that to something that is probability, something that we can interpret as a probability of each of the words in our vocabulary. And then we can just select the target from all of the words on the vocabulary. We can select the target, which are the ones that we are interested in. And then what this part seems a little bit magic. 4, 5, and 6 is first we do the logarithm of that, and then we do an average and then we change the sign. This seems a little bit magic, but the idea is that well, this is basically doing that, just computing that on the example of these 2 tiny batches that we have. And what we see is that if we do that, we actually get a number that would tell us that if we were training our system with these two sentences, it would give us a number which is 10, but I need to understand a little bit better what's happening here. So there is a reference here which is very interesting. It's actually in the book. It's mentioned by Sebastian, which is a YouTube video that he made about the loss function, and he basically explains that this is an interesting choice because let's say that h of x is the result of our last activation function of the, let's say that is the actual, the result of the softmax. So we already have the result of running the model and even the softmax and all of that. So we have this h of x. And now y is the whether each of the tokens of our vocabulary, we are going to say that y is 1 for the token that is correct, the one that we actually consider that is the right token, and 0 is the value that we are going to be assigning to every other token that is not the right value. We want to create a function that separates those results, what means h of x, as is a probability, it will add up to 1. So if we say that the result for the right one is 1, then for the other ones it must be 1 minus h of x, which means we are if this was a binary distribution, we are basically separating them. And Sebastian shows that this function actually does this job. It's a multiplication, and it's quite simple to understand why it does the job, because we just have to replace the y value in the exponents. So when y is 1, 1 minus 1 is 0. So all of this term becomes 1 because it's something to the power of 0. And this one becomes h of x, which is what we wanted in the first step. And when y equals 0, then this first term becomes 1 because it's something to the power of 0, and this one becomes 1 minus x because it's something to the power of just 1. So we get that function, and I think that the key here is that this becomes a product. And if this becomes a product, then one of the interesting things is that if we take a logarithm of that, then the logarithm is going to become an addition rather than a product, which is apparently easier to compute. And this is basically what we would have if you do all the operations and simplify. And the y here, this is actually what we would have for a number of samples, not only for one. Otherwise, it would just be y to the power of log. And the interesting thing here is that that for all of the terms that are not the right ones, this y would have been 0. So we could have another term in the summation for the y for the y's that are not the good tokens, but we don't care about those because it's 0. 0 to is a product that will always have 0. So basically, we have just the logarithm. And then Sebastian also mentioned that if we normally do the average, which is like dividing by the number of elements in each of our batches. And that's basically the way I understood, basically because otherwise the learning rate and other parameters are going to depend on our loss function. So if we increase the batch size or decrease it, we would have to be tweaking those parameters because the loss is going to be sensible to that. But if we do that this time, it sort of should be unsensible to these changes. So basically, this is going to be the idea. We have done it for the moment only. I mean, I executed this code, which I didn't go through it, but it's we are going through the probas is just the output of what is it here of the softmax. I mean, the model gave us some logits. We use softmax to unify to normalize them, And now we are using that to basically calculate the logarithm of that and do the mean and change the sign. So if we do that, I did it for the two samples for the two parts, and then I did it for the overall like if this was considered one batch and I did the whole training. And if we do call the cross entropy, we have to do some flatten, which is basically put the tensors in one only vector, and we get the same result. So basically, this is what we are going to want to use as our function for telling the system, because for every right token, it's going to give us the probability that it's going to try to maximize the probability to basically push it towards 1, because this is going to be, if to put it that way, whenever it said that a token was there, it means it was already estimating some probability, so we want to keep it, but for the rest of the tokens, we are going to assign a 0. So now we want to do this, but not with this text, but rather than with these two just short sentences, we want to go back to the text that we were using in chapter 1 and to the data loaders. So here, basically, we're just reading the verdict as and counting the number of elements. And here is just, we are going to choose, if we are going to train the model, we need to separate and have something to measure what we are actually training, but then we need to keep some part to be able to evaluate how the predictions would have worked in a text that is not the right the same that we use for training, because as we are going to see soon, the system is going to memorize everything basically. So if we used only some training data, we would think that we are doing perfect, but we wouldn't. So we separate here 90% of the text for training. And what we are doing is, these are just two text variables. This one contains the first 90% of the text, and this one contains the rest. And now we're using the data loader from chapter 2. I can go to the sources, so if someone wants, I would go there. I'm basically skipping the parts from previous chapters. So whenever we see something from this chapter, I will go in. But if anyone wants me to actually begin, I can go there. But here what we're doing is use the create data loader function from chapter 2 with basically some parameters to separate and to create a data loader for the training data set and another one for the validation. So let me run that. And now this is basically an inspection to see what would happen if we now executed if we iterate the train loader. We're going to have all of these batches with these sizes. And then for the validation, it just has some tiny remaining part. And now we have something new. We have the same functions that we were using before, the cross entropy. We want to use it to implement something that can validate one of those batches. So what we do is I implemented almost everything like classes, but this doesn't change much. It's just I separate the initialization where I received stuff like the model or the device from what's the calculation. But that's it just changes the fact that when I call the model, I have to do self.model or where I use device, because are things that I received through initialization function. But apart from that, this is the calc batch loss function from the book. And what we're doing is we are calling the model to gave us the logits, and then we are using the same thing that we did before, which is called the torch cross entropy function with the logits and with the target, which are which are the parameters of this function. And then we are going to build something over this, which is the loader loss, which is we are going to want to basically receive. Well, we're going to be using this batch loss function, but we want to iterate one of those loader, which we're going to receive here. And basically, the thing is done here, which is we have a total loss, which we initialize as 0. And then what we do is we iterate the data loader, and we run that function from before, passing it the input and the target batch, which is what the data loader is going to be giving us. And we basically obtain a number, which we have to call that item because it's a torch tensor of one dimension. So we basically get the number and we add it to the total. And at the end, we divide by the number of batches, which, by the way, I mean, it's a parameter, but I'm not giving it as a parameter generally because we have this code that Sebastian added, which what it does is if you leave it empty, it will just run the len it will count the things that are in that data loader. And if you actually say establish a number, then it also runs the len. But this means that you can use this if you actually say a number, but you can only use it to limit. So if we were using a data loader that has 3,000 records, we could call it with 100, and it would just do the first 100 elements. But that's it. We have, if we do that, we can run it on both the train and the validation loader. So we get some quantities, which at the moment, as these quantities are using the model and the model has not been trained, then we get still these big numbers that we were getting before. And now we're going to start actually trying to implement a training function. So we can start iterating this loader, calling this loss function. And we are going to need something, an extra piece, which is this.
Can I just ask a quick question?
Yeah, sure.
Can you go back to the average loss reported there? It's about 10 or 11. Can we just figure out what that number means? So it's something like the average of it's the average of the negative log of the probability. And if I'm just going to make up a number and see whether I can make it work. So if there were 100 things, presumably they'd be uniformly distributed amongst those 100 things. So each one should have a 1% chance on average. And so that has a log to base 10 probability of -2. And so the average of those, negative average of those should be 2. And is my thought process right? Is that how that number is derived? Because 10 is a big number when it's a log of something, or minus to the -10 is a big number. I guess it's an average, so no. So does someone else have an intuition about the scale of that number? With random data, we should be able to predict what that number is.
I do think that they talk about perplexity as well. And I think perplexity is actually used because it's more of an interpretable metric. And log loss it's easier to work with when you're training, but it is sometimes a little bit hard to interpret.
Okay. Is my rough way of understanding it that I guess okay, there's not 100 things there. There's 52,000 things.
Yeah, and I think most of it are very, very low probabilities. So the logarithm of a very low number is quite is relatively big. So for example, if you do like the logarithm of 1 to the power of -4 or -3 is -4. So I guess that's where the scale comes from, that you have a lot of things with very low probability.
But this is 10 to the -10 probability, and it's the average. So okay, I think we're all kind of vaguely right, but maybe not definitively right. Thanks.
Yeah, only thing I know is that we want this number to be minimized. So yeah, not sure why the order of magnitude. It would be interesting to kind of be able to estimate it and get to the power of 10 or something like that.
Okay, thanks.
Yeah, okay. So now to start implementing a training function, we need an additional piece that we haven't used yet, which is this thing called optimizer. We are using one that's pre-built, so we don't actually need to get to the internals, but basically is the piece of software that takes the output of the loss, this number basically, and decides how to change the parameters on the network. So rather than assuming that we have to always change all the parameters like what we are seeing is the definitive truth, we are basically telling it just with these numbers, we are allowing ourselves to tweak how much it should change the parameters and how much it should keep the values that are already in the weights of the system. So we basically, this is just, I'm just basically using the same parameters that Sebastian used here. If anyone wants to explain why the Adam W, I tried to get it, and I guess there are many things here like I mean, we're going from some easy. We could use here just gradient descent as the easiest probably optimizer, which only has, I guess, something like one parameter. But then we are basically using something that is more suitable for circumstances where we have multiple variables, so multiple maximums and minimums. So if anyone has an idea about why Adam is a good optimizer, I just know that it works, so I'm using it here. So then we want to write a function that actually iterates through the loaders and start using this optimizer and this loss function. So here's where we are now. We have a function. I'm going to the train function because basically the initialization is to receive all of that stuff, all of the optimizer, tokenizer, device, blah, blah, blah. So here is where we are actually going to be doing all the things. We start by telling PyTorch that we are going to be training the model so that it actually does take care of the gradients and all of that. And now we start iterating the loader. So we have this input and this target batch, so we can actually do the calculation. Here there are some functions that are basically, the way I see that is like how we tell both the optimizer that it should do the calculations on the with the loss to do the propagation back, and all of the rest is basically, all of this could be even removed because it's just we're going to be using it to write down information while we train the model. but it's not part of the training itself. So all of the things are happening basically here inside. We calculate the loss, and the system is smart enough to calculate all the derivatives of the loss, and and to quantify them against each of the parameters of our system, which is pretty cool because it's a lot of math that we don't have to do. And I guess this is just the way you tell it that you have done it. So the optimizer actually runs after we have processed the loss. So this is actually I am not doing any of this. It's just the optimizer of PyTorch doing the job, and that's basically it. Then we have this block, which is to print information every time we run one of these iterations. We have this evaluation frequency, which is a number that we are going to set. I think we have 5 or something like that, which is to tell it to just not do this block for every iteration, but for every 5 iterations or something like that. And what we are doing is we are running a function that evaluates the model, which is right here, which what it does is it calculates the loss for both the training and the validation set, and it does the calculation, and it gives back the numbers, so we basically can print them. So we are going to be running this, and we have the numbers. Apart from printing them, we are also going to be plotting them, which is, I guess, a little bit nicer. And that's basically this. That's basically the training function. If I run it, it will take. Oh, did I run the first ones? Oh no, I didn't run this one. Sorry. So if I run it, is in this case we are limiting this to 10 epochs. I believe that is basically because the text that we have is also not like a very clean and big text. So if we did more than that, we would not be getting much better results, I can presume. And we're going to see why. One of the things that we are plotting here is the result of asking it to complete the sentence. And it's not very logic what we're getting, but it's getting a little better each step. So at the end, we're getting things that actually look like almost text, although there are still some random things or things that doesn't look very well. But we can use now, we can check things here, like, for instance, the training loss and the evaluation loss, which they started being almost the same number, like 10 to the 99. And after the first iteration, already the train was being reduced, which is to expect because it's basically evaluating the model on what it has actually seen. So it's basically telling us that it remembers what it saw. And what I think is more interesting is that the evaluation loss is also decreasing at this point. But then we want to see that. So we basically have this plot where we see that basically we are getting stuck, and the validation loss is not improving since almost like the 3rd epoch. What means the system can remember more stuff if we keep adding more text, but we are basically, apart from I don't know where, but from around here, we are basically overfitting because it's not improving on the training, on the validation set, on the part that we kept. Because it's remembering everything we threw at it, because it's a very big model for such a small text. But anyway, we have now something a little bit better than before. If we try to read it, it's even something more or less readable. Every effort moves you. I was one of the picture. I felt his tone told me. we probably could see many of these parts in the text. I'm pretty sure that if we say we take subtext from here, we're going to find them in the text. But at least we are seeing words that are like a verb, then and it kind of starts making sense at least. But at this point, what we have is a model that if we start running it several times, in this case, what we have is just this is like a recapitulation of all what we did before. We take the same input as in the beginning. We use the text generator, which I call simple because we are going to create another one now that is a little bit is probabilistic. But at this point, we have this one, which just takes the most likely token, next token. And if we do that and call the generator generate, which is, I think that I did, it didn't show this function. It's basically calling, this is what Santiago did before, or the way I started the chapter, which is we call the model, get the logits, and then do the softmax and the argmax, so we get the most likely answer. And at this point, this is very predicted. This is very deterministic. If I run it a few times, I'm gonna be getting the same answer. So I keep running it, and it's quite insensible to the irony, blah blah blah. So we always get the same result. So now we're gonna start trying to make this a little bit more flexible, so we don't get every single time the same result. And this part starts is more or less like the same approach that Sebastian has. He starts with a very, very tiny vocabulary rather than the 50,000 words. So he chooses a set of words, and he assigned for each of them like an ID to identify each of them. This is basically so we can have this inverse vocabulary. So if we had a number like 3, we could say return forward. So the word that corresponds to each of the IDs. And basically here he's preparing, faking a tensor, like let's say that this could be some logits from the output of our system. And so we can use it in the same way that we would have done with the output of the system. But I guess he preferred to do it this way because it's tinier. We can see the whole vector here. And basically what we're seeing here is that if we do that, if we take one of these outputs from this emulates the output of our model, and if we run the softmax and the argmax, which is the strategy that we have been using in our simple text generator, well, we have the same thing. We have always the same result. I can execute it a million times, and it's always going to be forward because it's the greatest number here is, I guess it's this one, 675. So it's 0, 1, 2, 3, which is forward. So we are always going to get forward. And if we try to see that this is what we would have, basically the greatest probability would be no, sorry, this is already with scaling. Basically we are always going to get the greatest value, so we want to have more flexibility, and the way to do that is, well, this is just some plotting functions. I'm going to skip them, but here is what the strategy that we are going to be running, which is based on this multinomial function. Yeah, someone wants to talk? Oh, no, sorry. So basically what we're going to be using is this multinomial function, which is a torch function that basically receives a distribution of probabilities, and it chooses from that distribution a number of samples. So we're going to be using it with 1 because it's like we want to do something like the same thing that we were doing to get the next token. but it chooses one, but it does it by following the distribution probability that you give it. So basically, if we run it, I think that I'm going. Yeah, I'm jumping a little bit, but basically, if we run the multinomial 10 times and we give it these probabilities, probably more than 2 or 3 of the times it will actually give us forward because it's the most likely word, but it will follow this these probabilities, which is after normalizing. It will follow that probability distribution. So sometimes we will get the other words, which are I guess this is the probability with temperature one, which is basically undistorted. So we would have most of the times forward with normalized with these sizes. So forward would be with this distribution, there's a word that it would be returned probably half of the, no, not half, less of half of the time, but we get the idea. This would be the first, this would be the second, and this would be the third. So now we have, we want to start using this strategy to basically not get always the same result, but getting different results. I guess I will go back to the multinomial. I guess I'm going to go to the temperature first because it's what's actually here. The idea of the temperature, we saw this before in previous chapters. We are using here the softmax, which is this exponential divided by the addition of the exponential of all of the items in this case in these logits. And what we saw is that if we add a number that is a temperature here, what's going to happen is that if the number is tiny, then we're going to separate the most likely value from the other ones. In this case, this is with temperature 1, we have the undistorted plot. This is the values as they are returned by the softmax. And if we run the function with the softmax with this temperature .1, we are basically making the most likely value much more likely than the others and separating it from the other. And on the other hand, if we use a number that is greater than 1, what we're going to do is to push the less likely values up. So now we have a number that we can use to make the distance from the most likely value to the, let's say, second or third most likely values shorter. So basically, if we run this, which is what we're going to be doing, we can add a temperature, which is, generally speaking, we're going to use a positive number always for the temperature so that we get this effect. And then we can basically sample and take from here some of the most likely values, say 2 or 3. So we would, if we use a top 3 here, we would be getting here the 3 most likely values, which is forward, toward, and closer. So basically, that's what we are going to be doing here, which is to use complement the previous temperature and softmax with this top K. The top K is basically that we choose a random number, in this case 3. So if we use the top K PyTorch function with the token logits, which is again this basically on this distribution, we are going to be getting the 3 most likely ones, which are toward, forward, and closer, which is basically the 3 ones which with the greatest values. And now we can change our, well, basically, rather than changing the text generator, I created a new one which is rather than simple text generator, probabilistic text generator, but it's the same idea again. And what we're going to do now is this is the new thing here, basically. First, if there is no top K, then we just get the logits as we did before. And what we would do with this is the normal softmax and argmax. So if there's no top K, then it doesn't change. But if we actually do set a top K, then we get the logits. With this, we're gonna get the third one. If we set, assuming the top K is 3, we will the kth one. And so that is the minimum value of the number of K elements that we chose. And then we torch where we are gonna basically get all the ones that are above that value. Which in the case, if we were here, it would be like first we take with top K equals 3, we would get the value of closer, which is 0, whatever. And then by filtering greater or equal than that probability, we will get these 3 values, the 3 most likely values. So this is like we would be using this to filter the logits. So then we also combine this with the temperature that we had before, which is basically if there is a temperature that is greater than 0, because if it's 0, we would get a division by 0. So if we have something, we do the divide by the temperature, and then we do the softmax and the multinomial. So this is the combination. In case we say the temperature is 0 or don't add any temperature, then we would get the same logic that we had before, which is it would just get the logits, and then it would take the argmax, which, by the way, I did this at the beginning of the presentation here. I skipped this part, but it's basically when we call the model, we can do the softmax and the argmax. But if we are following this strategy of taking the most likely element, we actually don't need to do the softmax, because if we do the argmax of the logits directly, it's going to be the same. It's going to take the maximum argument, and the softmax does not change which element is the maximum. So that's something that is happening here. If there is no temperature, we actually don't need to do this. We can go directly to the argmax of the logits. And then here there is something I don't know if you guys realized, but I saw this came from the book. I mean, Sebastian doesn't use self because he does a functional approach. But anyway, there is this I guess end of string ID, which is never actually used, because when we call the function is kept to none. So at the end, I don't really understand. I think this must be something that probably wasn't actually used, but I don't know if anyone knows, but to me, it's something that is there just uncompleted. And I guess we could have something like the tokenizer recognizing the end of a sentence, so it stops when it finds it, but it's never going to do that because we are never using that value. So just in case anyone found that. So at this point, we can use this probabilistic text generator. So what I'm doing is I did it 10 times, because why not? If we want to check that it gives us different values each time, then it makes sense to actually make it generate more than one sentence. And this is what we are seeing. Actually, what's interesting is that the text is going to be different because not only one time is different, but if as this is a loop and we are getting probabilistic each of the times, even if the first time it got this sentence, when it's executed again, if in other part we had also, like here, for instance, we have in 2 times, but this time it decided that the most likely token was a dot, and in this one it decided it was an I. So it's going to be probabilistic in each of the tokens, so the sentence is obviously going to be much different. So at this point we have more or less the model ready for generating different values each time, which is pretty cool. And now we can we go to the next part, which is storing it, so that we can basically save. We have a state now that is living. In this case, is living in this variable model in my Jupyter notebook. But if I close it and I open it again, it's not trained. It's not. I forgot everything. I would have to run this step, which is the training one, which is obviously the most expensive one in terms of computation. So what we want is to actually be able to save the parameters. And here there are two strategies. I didn't complete the last one, the OpenAI one. Now we will get to that. But the first one, which is the one that we can use for our trained model, is to just call this torch save function, which if I do, then it generates a file that I'm saving here, which is this model PTH, is 600 megabytes. I guess it's going to be the same size always, because it's just we have a fixed number of parameters. And then we can load the model. But before doing that, Sebastian also says that this only saves the model, but the optimizer that we prepared has its own parameters that also change. So if I wanted to save this and keep running the training process, it wouldn't be enough with this model, because I'm only storing the part of the parameters that correspond to the model. So, but rather than that, we can store. We could save 2 files with model and with optimizer, changing optimizer here rather than model, and obviously here. But apparently, the save function can also receive a dictionary, so we can add a key called whatever, let's say model and optimizer, and if we run it, it's gonna store all of the weights this time. So now if I go here, this time we have this. I am surprised because it's even bigger. It seems like the optimizer takes even more space than the model. The model is 600 megabytes, and the model and the optimizer is 2 gigabytes. So apparently the optimizer stores a lot of information. And now we can finally load the weights. So these 2 files that we generated. The easiest way is just to use load state dict and torch load. Basically, torch load is going to read the file and give us a Python dictionary, and load state dict is going to store, basically load the model from each of those parameters. This is just doing it from the model, not considering the optimizer. And in this case, if I want to load both the optimizer and the model, I have to first create the way the procedure. I'm basically repeating the whole procedure. We would have to instantiate the model again, new from scratch, with the same number of parameters, and also the optimizer. And then we can load them by basically doing that. Reading with load, we would get a dictionary, and then we could take the keys of the dictionary, each of them, to load both the model and the optimizer. So if I do that, it's pretty quick. And now I could use the loaded model as if it was the trained model. I have completed up to here, because then the next part we can discuss it, but I'm having some issues here, which we can discuss if you want, related with the sizes of the layers.
I just had a quick question about the loading process.
Yeah.
Does it end up having 2 copies of both the the model and the optimizer state in memory at the same time, the way this is loading?
Well, that's I guess in this case I loaded with a different name. I guess I should just use the same model word, so we would be getting rid. But in a production
So in the just going down a little further, it says checkpoint equals torch load. So does torch load actually do the loading? Or is it just set it up to load and then
no, torch load only reads the checkpoint, reads it reads a file basically and gives you a dictionary with the values, and then this is the functions load, state dict, which are in the model and in the optimizer. These are the ones that change the state of the model and the state of the optimizer.
So those are the ones that actually probably do the actual load, and so it's probably only once in memory.
Yeah. Yeah.
In the book, I think the author does say that the model is loaded with random parameters. So it might be that there is a copy, it's two copies, but it's overwritten once you load the state dict.
I'm just wondering whether it takes, instead of 600 megabytes, 1.2 gigabytes, or more interesting when we use the 1.5 gigabyte version, whether it's too big. But if it only loads once, it's probably fine.
Yeah. Yeah, now for the next part, well, I'm gonna get into the next part, although I didn't complete it because I got like an error. But the next part is basically there is a script that is GPT load, which is a script that Sebastian wrote for us, and he oh, it's not here. Sorry. It basically downloads the weights from this server, and it allows you to choose which of the sizes, the small or the different sizes of the GPT-2, and then it gives you back some values, but this is different from what we did before because apparently back then OpenAI used TensorFlow rather than PyTorch, so we need to do some crazy conversions. But basically, if we use Santiago's functions, we just have to choose one of the models. I chose the tiniest one because otherwise I think my computer would probably die. But if I run it, it's smart enough to not download twice because I did it already. So it's telling me that each of the files is already in my computer. But this is basically it. You just have to choose the model size, which is one of the keys from here. One of the keys, you choose the size, and it will take all of the files, and it creates a folder in your wherever you tell it to download the files. It will create a folder for the model, and here's where we have. So I guess if you run it with different models, I didn't do that, but I guess it would create just different one folder for each model, and then let me go back here. We have to do the same thing again. We have to create the GPT model. I am doing here, I'm using GPT config, which is I created a small class here, which stores the values. And then I added some static method with these are enumerations that he has at the end of the chapter for each of the sizes. So for the small one, these are the parameters that we should be apparently using. So I'm basically creating a model with that with those small parameters. Then he runs eval. I think it's just to return this sort of array where you have the information about the size of the layers, I guess. And then he created this assign function, which is basically to rather than take the parameters. I didn't say that, but when we call this function, what it's giving us is this settings and params, which is the params is where all of the weights are, and this is what we want to put into our model. So to do that, he creates a very big function, and this is why I'm having problems, because when I created all of these classes, when I created basically, for instance, the GPT model class, I renamed some of the things like token embeddings. I use this string token underscore embeddings, because at that moment I thought that this didn't have consequences, but now I saw when I saw this function, I had to tweak it, because you need to actually know the relationship between all of the things that live in the params, which is what we read from GPT-2 from OpenAI weights. You need to know the relationship from that and each of your parameters in the model. That also happened with the attention layer when we created this multi-head attention class, for instance. I'm not sure if I renamed all of the things, but in some cases I renamed some of the variables. So now I have to take care of all of that. I think that I did, but the problem is that now I'm getting a shape mismatch, which is every time he assigns the values, he calls an assign function, which what it does is make sure that you have the right dimensions for each of the elements. It's the only thing that it does. It basically you're gonna give the left side and the right side, and it checks if they don't have the same shape, then it crashes. So you don't assign something of a different size, basically. And at this point, I'm getting something which I'm not sure if I did something wrong, but if I try to run it, this is what I was telling you, why I couldn't complete it. For the token embeddings layer, the left side, which is what I created, has a 2 dimensions, which is the vocabulary size and the embedding size. But the right side for the this is the wait. I think that I got it. This is I guess this is token embedding and position embedding. I'm assigning them the other way around, I guess. Now I don't have yeah. Okay, that was it. Okay, apparently now I have the weights, so I should be able. I didn't complete because I had that mismatch. Sorry. But apparently now I should have GPT as a model with the weights. So if you want, we can try to take one of the generation texts. Let me copy something from here, for instance. Something like this should work. And let me add it here. Only that rather than model, I would use this thing called GPT, I guess. Not sure what will it happen. Oh, there we go. Nice. So now we have something that actually makes sense, I guess. Every effort moves you up. I am sorry, and I am sorry that you need to see that. And I am still praying that, wow, that's beautiful. Okay, now we have something that kind of makes sense. I'm sorry, I was making this mismatch of the embedding and the position embedding. That's why I had that. But this is interesting. The thing is that as we are using here weights that were stored with a different system, we have to manually assign each of the values from the dictionary to each of the values in our model. So it's a little bit more, how do I say it?
Annoying.
Annoying, exactly.
Yeah.
But I guess once I have done this, something that I should be able to do is to store them again, I guess, like GPT-2 PTH, right? So that if I want to load it again, I can have it in the right format. So that should be easy to do if I do something like, well, if I run this right now, it should work. Only that we are not. This is a question also that I had when I saw this part, the OpenAI part, is that we are loading weights, but we are not loading anything on the optimizer. Which I don't know if they published weights for the optimizer. I guess it does not even make sense what I'm saying. But when we do this blog, we were loading, but only with PyTorch. Sebastian said that this thing about the optimizer having its own weights. So that's why he recommends us to do this way of saving and storing. But I guess when we load from a different system, maybe we don't have those weights. I don't know. That's interesting. I'm going to try to save the model with this. I guess this should do it, right? If I just add here another model, in this case is GPT, so I'm gonna call it GPT-2, and this should give me a file that I can restore, right? But with the, just in order to, if I want to do it again, not have to use this mapping function, so I can use this file, which is again 700. It's not exactly the same size, but I guess the values also. Maybe I have a lot of zeros in our model. I don't know. Well, this is it. Basically, that's the whole chapter. So I hope that you had fun.
No, it was
Any
it was
questions?
it was pretty cool. Yeah. Okay. I have maybe an answer for Peter's question, or I don't know if an answer, but I did an experiment to show the reasoning of the scale of the loss from random numbers. I don't know if you would like to see it, unless first you have any questions for Carlos. No? Then yeah.
You want to share screen or something to?
Yeah. eh, Thanks a lot, Carlos. That was amazing. The live speaking part was impressive. I'm pretty happy to see that you make it work. So I was playing with uh, with the question from Peter, and why does the loss is like around 10, if we have like some random numbers. So I did an experiment. I created like I sample a random like 10,000, is it? Yeah, 10,000 numbers from a uniform distribution, and I just turn them into probabilities uh, by doing this. So if I run this, I get 10,000 numbers. The sum of them is equal to 1. This is just 4 of them. So we have like 10,000 of these kind of similar numbers. If I plot this distribution, we can actually check that it looks like a uniform distribution. And then if we start doing like the cross entropy loss, I calculate the logarithm of these probabilities, and it looks like this, right? Now, things are in the order of 8, 10, 9. And if I calculate the negative, of course, it just turns this into positives. And then the average of this is the actual loss that we're using during training, which is also called cross entropy. And it's in the order of close to 10. So what happens if then I only use here, for example, 100, I don't have a context or a vocal
or 50 or 57,000.
57,000.
So the number in the vocabulary, I think, is the right number.
I get something close to 11. If I then go to the extremes, right? If I just do 100, and then I do this, we should expect to see a lower loss, which is relatively low, yeah. So the random initial loss, it's dependent on the vocabulary size, basically. There's kind of a dependency there. If I just have a bigger
And
vocabulary.
I think that's also why perplexity is nice and interpretable, because that is in terms of the units, there is kind of your vocabulary size. So if your perplexity actually tells you sort of on average how many like tokens in your dictionary the model has to consider as for each prediction. So if perplexity is like 57,000, it's kind of randomly distributed. But if perplexity is 10, it means it's only looking like on average at like 10-ish like candidate tokens to predict the next one.
So yeah, hopefully this clarifies a little bit or helps the intuition with that, Peter. With your question.
Could you please share the notebook? This is cool to play with. Thank you.
Then I'm gonna show it. Well, you wait for me to share it. And I wanted to thank again Carlos. That was a really good job. And thank you a lot for taking the time for doing great like tutorial like explanation. And so next week, so first two topics that I wanted to discuss. Let me open my calendar. We are heading towards chapter 6, and there are 7 chapters. Next session would be scheduled for 22nd of December, and I don't know if we're gonna finish actually the book on the 29th, but we could aim to do it. But I don't know if like everybody is able to join these 2 Sundays because it is very close to Christmas. We are all in different time zones, so I don't know if it makes sense to still have them here or not. What are your thoughts on that?
So I know I won't be able to join in person for the next 3 Sundays.
3 Sundays. Okay.
Yeah. Christmas and travel.
Should we take a break for the next 2 or 3 Sundays? But don't lose your momentum.
That's the thing. That's the thing. I will be losing lots of momentum, but I don't know.
To me, it's a good moment actually because we have something now to start tweaking. After I finish this chapter, there's a lot of things from previous chapters that we have been talking about, like where are facts stored or whatever, that now I have ideas like, okay, now I can prepare a very, very customized data set to train a system with only certain things and try to see, to plot stuff. So basically, I think it's a good moment to do something, a little pause, and then came back with a little bit of recap, because also the next chapters are also going to be very, very practical, I guess.
Mm-hmm.
Can I throw us
yeah.
a motion on the floor? Why don't we take a break for the next 3 sessions, but either this coming Sunday, the 22nd, or the 29th, one of them, we can just have a group meeting, not to cover any sessions, but if anybody wants to do exercises, just like, hey, I tried this over the next couple of weeks, let's play around. Here's what I thought. Can somebody help me? To even stupid questions. One of the things that happened for me, even as I was coding and preparing and following along here, my entire Conda environment just blew up. Like I ruined everything. I am paying for Google Colab and I'm going, I don't want to pay for Google Colab anymore, Colab Pro. I'd rather have everything running on, say, AWS or Google environment entirely. So it'd be nice to have a session where some very smart computer science, like engineers, could walk through stuff like that and just open themselves up to sharing some of those ideas and learnings. Maybe on the 29th, we can have something just friendly, hey, tech review session, not about the chapters, but like, or it can be about the chapters, it can be about X. Anyway, I'll be quiet now.
That's a good idea. That's a good idea.
Okay to me.
Yeah. We do it that on the 29th.
Again, no particular date if anybody's interested. It's up to the group. It's up to the group when we would do it. I mean, Christmas is coming up and then New Year's. Maybe if they're, Peter mentioned he has travel. Don't put you on the spot, Peter. But if anyone's around, we can just sort of all have an interesting jam session, but not about necessarily on this material unless anybody has questions. And it's to help one another more than anything.
I like 29th also because it's like kind of in the middle. So
Mhm.
I guess it helps not losing momentum.
Yeah.
Yeah. Good. Then let's do a short meeting on the 29th. Smash that, and we get back on the not the 5th, but the week later, the 5th, right?
Okay.
That's the idea.
Mhm.
And on the 12th, okay, I'm gonna write that down so later send it on this one, so everybody has it. Okay, that's great. That is great. Should we assign a volunteer for like first real session for next year? Because it will be hard to then find a volunteer.
I can volunteer.
You can do it, Michael? Great.
Hey, Michael, thank you.
Sure. So that's for chapter 6, right?
6. Yes. It's in
Yeah,
the
okay.
fine-tuning for classification. Nice. All right. So, yeah, happy holidays.
Yep. Happy holidays, everybody. Michael, if you need any help with background support for chapter 6, let me know.
Okay, thank you. I appreciate that.
All right. See you for everybody that wants to join the 29th. Yes, happy holidays. Enjoy next Sunday, morning or afternoon or night. I actually don't know. We'll have it free. So wait. Yeah. Thanks all for joining.
Yeah.
Thanks.
Happy and safe holidays, everybody.